Okay, so you know why GLUT1 is important? Because glucose can be transported inside, and then it can be used to make ATP. Yeah.
Okay, I just have a question. Okay, so going back real quick before, what was your question? I don't remember.
He's asking if your carbonic anhydrous is
Yeah.
Attached to the band 3.
To what?
banned.
Attached to band 3.
Yeah, they could be, yeah.
It is.
Yeah.
So what would be attached to the C terminal?
There's free-floating carbonic anhydrous, and there's surface-attached carbonic anhydrous.
Does it end up being released once chlorine enters? Or it has
There's
no-
different varieties.
Okay.
Yeah, we'll discuss them tomorrow. It makes no difference anyways. So you can have carbonic, if this is band 3, you know, I just don't want to take away from this because this is, let's say, band 3. Carbonic anhydrous are attached here. Some are free-floating, some are disfloating. There's different varieties of it. It's not always like clear-cut.
So it's not really too relevant.
No. The function is relevant, not the location. Yeah? Okay. All right, so next thing that can happen to glucose is very, very important. Glucose can be converted to glucose 6-phosphate. Let's just say once glucose goes in, automatically it's converted to glucose 6-phosphate. That's the most important state of glucose inside the cell. The intracellular form of glucose within the cell is always glucose 6-phosphate. Remember that. The intracellular form of glucose, intracellular form means what? The type of glucose that's inside the cell. The intracellular form is always glucose 6-phosphate. Always, always, always. Otherwise, it will leak back. See, phosphate is highly charged, so it traps glucose. Not just glucose purely without the phosphate will be outside in plasma. Okay? So this glucose 6-phosphate, the next process known as hexose or pentose monophosphate shunt. This pathway, I know I'm giving you a headache, I'm sorry, but you got to do it. Once you memorize, it's only 2 steps in this pathway. Once you memorize it, it becomes so easy because this is so relevant. This is extremely high yield, especially from people from the Mediterranean area. Egypt, Morocco, Italy, Spain, Portugal, Algeria, all those countries share something in common, and that is this pathway. All of us have it, but they have the defect of it, okay? That's what I meant. Okay? They're most likely to carry this mutation of this pathway. So the pentose monophosphate shunt or hexose monophosphate shunt, they're both correct names. Glucose 6-phosphate. Glucose 6-phosphate is converted to 6-phosphogluconate. And then 6-phosphogluconate is converted to xylose. Oh, why am I saying xylose? Yeah, you could say that. Is it 5? Xylose 5-phosphate, I think? I think so. I don't know why I'm forgetting this. Xylose 5-phosphate. I think so. No. What's the sugar that's used for DNA synthesis? Ribose. Thank you. Ribose, yeah. Ribose. Ribose or ribulose, same thing, but ribose 5-phosphate. There you go. Okay. This whole cycle is known as shunt. Shunt is usually not used unless you have too much glucose. Okay, shunts are meanings rediverting. It's not the primary pathway. Shunt means rediverting. If you have too much of something, then you can divert it to something else. Okay? So when it comes to RBCs, this pathway also occurs within RBCs. It's important. Why? Okay, this pathway produces NADPH, both enzymes. NADPH. Okay, so the enzyme number 1 is known as glucose 6-phosphate dehydrogenase. So the enzyme here is known as what? Dehydrogenase. What dehydrogenase? Glucose 6-phosphate dehydrogenase. One of the most important enzymes that you need to know in medicine. Glucose 6-phosphate dehydrogenase. You see the enzymes are always named after what? The substrate. What do we start with? What did we start with? Glucose 6-phosphate. So the enzyme is named after this substrate. So it's glucose 6-phosphate dehydrogenase. Dehydrogenase. Let me write down dehydrogenase for you. Whoa. Dehydrogenase. What does D mean? Removing, without. What is hydrogen? Let's combine them. Hydrogen. Ase. What does ase mean? Enzyme. Enzyme that removes, this means remove, and this means hydrogen. So dehydrogenase, what do? They add or remove hydrogen. That's all they do. And NADP is a hydrogen carrier. It's nothing more than a hydrogen carrier. That's all it does. Don't make it too complicated. NADP without the hydrogen. NADP. This molecule is nothing more than a carrier of a hydrogen. This hydrogen carries a lot of electrons, so it's helpful. Okay, we'll see how it's helpful right now, okay? So the first enzyme, what would you call it? Glucose 6-phosphate dehydrogenase. The second enzyme, what would you call it? 6-phosphogluconate dehydrogenase. I don't care for the ribose 5-phosphate right now, although it's used for DNA synthesis and RNA synthesis. Okay, I don't care for it now. If you know it, amazing. Congratulations, okay? What do I care for? This pathway gives me or generates for me, where is the light green? There you go. This is what I care for. It gives me NADPH. That's all I care for. This pathway is useful to RBCs. Why? It generates NADPH. It generates what? NADPH. And NADPH is a hydrogen carrier, a hydrogen ion carrier. Okay. So how can we make sense out of this? We no longer need glute. Okay, so I don't need glute. We need something else now. On the surface of RBCs, we have another protein. Okay, on the surface of RBCs, we have another protein. This protein is known as glycoprotein inositol 3 or GPI3. G stands for glyco, P for protein, I for inositol 3. There's one more protein found on the surface of RBCs, GPI3. You have to memorize that. When people don't have this protein, they will have anemia. They will have anemia. The anemia is known as nocturnal, paroxysmal hemoglobinuria, meaning nighttime hemoglobin builds up in the urine. That's what it means. We'll discuss it. It's okay. Okay. Nocturnal paroxysmal hemoglobinuria, or NHP. Okay. So now, you know what this enzyme does? I mean, this protein on the surface, it deactivates complement. It deactivates complements. Okay? This GPI3 deactivates complements. That means MAC, if MAC is there, it can attack this RBC and lyse it. But who will protect the RBC from MAC attack? GPI3. Okay? All right, so one way you can lyse RBCs by which pathway? Complement. MAC attack. Okay? So GPI3 protects the RBC at all time from who? From complements. Does that make sense? Look, you can have infection. When you have infection, complements gets activated. How come your RBCs are still protected? Who protects it? GPI3. Okay, is that okay? Okay, so that's one thing. So one way you can damage RBC is by complement damage. Another way you can damage RBC is by free radical production. So the reason I mentioned this at the same time, although GPI3 has nothing to do with NADPH, I had to mention it because there's two ways to damage RBCs. Healthy RBCs. One is by complements and one is by free radicals. Are we okay so far? There are two ways to damage red blood cells within blood vessels. Healthy red blood cells. Free radical and complements. Free radicals are a normal product of metabolism. Free radicals are normal products of metabolism. Some product might produce, like some food that you eat, might produce more free radicals. like fava beans. Okay, so let me get rid of this right now, so at least you understand GPI 3. Now we're going to talk about free radicals. This is an oxygen free radical, okay, and this is perchlorate free radical. Yeah.
Real quick, if you don't mind, for the NAD pH, for the NAD pH, is the hydrogen is that used for hemoglobin? And then
I didn't say anything yet. I'll tell you. Yeah, I didn't say anything. So I know what NADPH. I'll just tell you when. Just give me a second. Okay. We are not done yet. Yeah. So free radical can cause damage to who? To RBCs. Know something about free radicals. They cause lipid peroxidation. This term you have to know. Peroxidation. This is what free radicals do. Free radicals, no matter which membrane, it will cause it to get destroyed. It causes lipid peroxidation. The term lipid peroxidation leads to lipid or phospholipid membrane damage. If it wasn't for some mechanism to protect our cells, we will always have destruction of any cells, any cell membrane. Okay? So you see other cells have mitochondria, they have peroxisome, they have lysosomes, they have endoplasmic reticulum, which can protect against free radicals. Look what I'm telling you. Protection against free radicals is done by who? By mitochondria, by peroxisomes, by endoplasmic reticulum. Is that okay? Protection against free radical damage in your body is done by who? Mitochondria, peroxisomes, endoplasmic reticulum, which RBCs don't have. So all other cells are protected. RBCs are not protected so well. The only thing that can protect RBC from free radical damage is something known as glutathione. Glutathione. Okay, glutathione. Usually they have a group known as SH. Glutathione. Glutathione protects against free radical. One more free radical, you can call it hydrogen peroxide. It's not a completely free radical, but it is a converted to free radicals. Okay. So who neutralizes these free radicals? Glutathione. Okay. Now, those cells that have mitochondria, they'll metabolize them and neutralize free radicals by different pathway. Those cells that have endoplasmic reticulum will neutralize by a different mechanism. Those cells that have, what's the other one? Peroxisomes will neutralize by catalase, for example. But RBCs don't have that. The only mechanism they can use to neutralize these free radicals is by what? Glutathione. It's a group of enzymes. You guys also heard of P54, right? P450, sorry. Right? Which is primarily found in what? Peroxisome and endoplasmic reticulum. But RBCs don't have them, so you cannot neutralize free radical by this pathway. It's okay for now if you don't know this. But just know this, in RBCs, the only mechanism that can neutralize free radicals is what? Glutathione. Free radicals, you know, once they start, they don't stop. It's a chain of reaction. If you have one free radical, they can produce more and more and more. It keeps increasing and increasing and increasing. And they produce lipid free radicals. So why did I erase it? I don't know. These free radicals can cause lipid peroxidation. So we'll have lipid free radicals floating around. And they will cause even more damage and lead to cell death. So we need to protect against these free radicals. Again, free radicals are produced. It's a normal process in your body. They are produced in some quantity, but you have a mechanism to protect yourself. Okay? All right. Glutathione requires NADPH. For glutathione activation, what do you need? NADPH. For glutathione activation, what do you need? NADPH. And who's providing that? Pentose monophosphate shunt, which is glucose metabolism. So the reason I mentioned this step is that the only way RBCs can protect themselves from free radicals is what? Through pentose monophosphate shunt pathway. Okay, although there's many steps, but as long as you understand the idea. So for protection against free radical, what do you need? You need NADPH and glutathione. Directly you need glutathione. But glutathione needs what? NADPH. Okay? So glutathione exists in two forms, although it's not significant, we don't care for it now. Oxidized form and reduced form. Those of you who took organic chemistry, you know oxidation and reduction. The reduced form is what can protect against free radicals. But you need NADPH to reduce glutathione. The oxidized forms cannot help. So if you don't have NADPH, all glutathione will exist in what form? Is the oxidized form. As a result, I'm getting blah, blah, blah. They cannot protect you. So at the end, don't worry about the biochemistry of it so much. Worry about the concept. For RBCs to protect themselves against free radical, you need two factors. Directly glutathione. Which form? Reduced form of it. And for the reduced form, you need NADPH. NADPH is produced by what? Glucose 6-phosphate dehydrogenase. Now, why did I mention Mediterranean people? Mediterranean people are most likely to be deficient in this enzyme. Not all of them, but it's more prevalent in that population. Just like sickle cell anemia is a predominant disease of African American, just like cystic fibrosis, a predominant disease of Caucasians. Now, glucose 6-phosphate dehydrogenase deficiency is primary disease of Mediterranean people. Okay? Make sense? Just like Crohn's or ulcerative colitis is a primary disease of Afghans. You know? So every group has some sort of condition that's more prevalent in them. Okay, so I mentioned that every exam has this question. Every exam. There's no step 1 exam that has no question on this. So, people who are glucose 6-phosphate dehydrogenase deficient, they're at risk of what? Free radical damage to RBCs. And then when the cell membrane is damaged, what happens to this RBCs? It's no longer flexible. It's no longer biconcave. It's what? Spherical. And it ruptures. So glucose 6-phosphate dehydrogenase will lead to hemolytic anemia. Hemolytic anemia. Hemolytic anemia. Okay? Yeah. But people who carry this mutation, would they always have hemolysis? No. I'll discuss the disease more. So the only time they were more at risk of hemolysis if they have more than normal free radical production. And we'll talk about the factors that increases free radical production. Okay? So I'm done with this. Two processes that are very important in RBCs, glycolysis and glucose 6-phosphate dehydrogenase pathway for different purposes. Glycolysis for ATP production, maintaining cell, and glucose 6-phosphate dehydrogenase for protection against free radical. Are we good? Okay. And the only thing left is, I think, the ABO. Okay. Let's say this is RBC. Now, RBC would have on their surfaces, their cell membrane is made of what? Phospholipid bilayer, right? Okay. Phospholipid bilayer. Okay. So we have two chromosomes. What I'm talking about right now is antigen A, antigen B, and antigen O. There's no such thing as O, but let's call it antigen H. That's what it's called. Okay? And the last one was antigen D. Okay? These are the antigen that are used for identifying blood types. Blood grouping is based on these antigen. If you have blood group A type, you have A antigen. If you have blood group type B, you have B antigen only. If you have AB, you have both. If you have O, you have H antigen. And if you have D, you have RH antigen, or D antigen RH group. That's like the positive and negative. So the D gives you the positive type or negative. A will be A type. B will be B type. AB is both AB. H is O type. So H is, what type of blood is H? O. What type of blood is type B? B. And A? If you have both A and B, AB. If you have D antigen, it's positive. If you don't have it, it's negative. Okay? Now these antigens are primarily made of sugars. They're sugars. Except D is a protein. So D is a protein. Okay? A, B, H is a sugar. It's oligosaccharide, multiple sugars attached, and then D is a protein. So let's talk about AB first, okay? And then I'll talk about application. First, let's identify it. Okay, the H antigen is made of a galactose attached to N-acetyl glucosamine attached to, what's the other one? Galactose again. I'm missing something. And then I think fucose. Yeah, fucose. There you go. There's one missing. I'm missing one. Oh, it's okay, but don't matter. Okay, this is known as the H antigen. So then it's attached to the cell membrane. Let's say this is the cell membrane. If it's attached to a lipid, it's a liposaccharide. If it's attached to a phospholipid, it will be a liposaccharide. It could be attached to a protein. If it's attached to protein, what do you call it? Glycoprotein. If it's attached to lipid, glycolipid. Okay? It's attached to a membrane regardless. But it could be attached to a lipid or a protein. If it's attached to lipid, liposaccharide, because saccharide means sugar. If it's attached to a protein, it's glycoprotein. Glycolipid, glycoprotein. Okay? So those are the names you should use. You can use saccharide too. It's okay. Liposaccharide and proteosaccharide. You can use those two. But glyco is better, glycoprotein, glycolipid. So it doesn't matter which one is attached to, but regardless, it is constant. It has galactose, N-acetyl glucosamine. N-acetyl glucosamine. You've seen this before too, right?
Yeah, in the
Peptidoglycan? Good job. N, so this is how you should write it. N-acetyl, that's L and then dash, glucose, amine. That means this glucose has a nitrogen attached to it. That's the amine group, nitrogen. Glucose is glucose. Acetyl group is CH3. Attach and position N. That's all. But as I said, for now, just don't worry about this. Know that NAG stands for N-acetyl glucosamine. It's a sugar. Galactose is a sugar. There should be glucose somewhere, probably. I forgot. I think it was made of 5. I'm forgetting the last one, but it's okay. This is the important one. The last one is fucose. Okay. Now, if I attached to this H antigen, if I attach to this galactose, this is considered B antigen. Okay? Look, the H antigen is a precursor for what? A and B. The H antigen is a precursor for A and B type. You cannot have A and B without H. That means all RBC should have H. If you modified it to B or A, it depends. If you add a galactose to it, what does it become? Type B antigen. But what if you add, instead of galactose, you can add something else? Let's use green this time. You can add to it N-acetyl galactose. See, galactose and N-acetyl galactose, two different things. Slightly different version. This would be type A antigen. Now, how would you remember? At least know acetyl has A. That's type A. Just galactose by itself is become type B. If you don't add anything, it's type O. Okay? Yeah. Just remember the sequence, then it will become easier. Can you memorize the sequence of the H antigen? Okay, memorize this one, please. I'm missing one of them. It should be 5. Yeah. It's wrong. Yeah. It will attach to, okay, no, sorry. Hold on. So this is fucose, galactose, and then N-acetyl glucosamine, and then galactose again, and I think the first one is glucose. There you go, maybe. Okay, the sugar is attached to here, you're right. It is attached to galactose, not to fucose. Okay, yeah. The addition is done here. Okay, so we want to identify these antigens. How do we identify them? Look, you can add to galactose N-acetyl galactose. If you add this, you cannot have two at the same time. You either add N-acetyl galactose or just galactose by itself. Galactose. Galactose is a sugar as well. If you add only galactose, that's considered type B blood. If you don't add galactose and you only add N-acetyl galactose, then it's type A. If there's none of them, let me erase them both. If none of them, that's type O. Okay? So to make it simple, I'll do this. So let's say we have the H antigen. Okay, so this is the H antigen, H antigen, and H antigen. If you attach to H antigen galactose only, that's something else. If you attach to it N-acetyl galactose, that's something else. If you have nothing attached, it's something else. So there's three types possible. If nothing is attached, this is known as type O blood. If N-acetyl galactose is attached, it's known as type A blood. If galactose alone is attached, then it's known as type B blood. Make sense? Okay. But attachment has to be done by who? Enzymes. So it means you need enzymes for that. Okay, so we'll come to that. Now, in order to identify A, B, O type blood, you base it on this. Depending on the surface of RBC. If on the surface of RBC I only have H, what type of blood is that? O. If on the surface of RBC I have only N-acetyl galactose, I mean plus H, right? So should I put H just to not confuse it? Let's just say H. Here we have H plus N-acetyl galactose, type A. So this is A, this was O. In another case, we have the H plus we have galactose, type B. Make sense? So that's how you identify the types. Now, the positive and negative depends whether an RBC has the D antigen or don't. If they have the D antigen, it's considered positive. If they don't have it, it's considered negative. I'll give you all the scenarios, but as long as you understand for now. So O can be positive or negative. Depends if they have D or they don't have D. A can be positive or negative. Depend if it has D or no D. Same thing with B. So total, there's how many types of blood? And then you have AB as well. What's the total? 8 types. So AB positive, AB negative. A negative, A positive. B negative, B positive. O positive, O negative. Make sense? Yeah? Okay. I mean, I forgot. Look, there's one more. If they have the galactose and the N-acetyl galactose at the same time, that's AB. That's AB. Okay? Yeah.
So do they have to separate each antigen different alleles?
I'll come to the genetics. Let's just understand the structure first. Okay? I'll come to the genetics of it. Yeah.
Where does the B antigen go?
Huh?
Where does the B antigen go?
Oh, that's separate by itself. It's a different location. Okay? Now, it will make sense. You see, the gene for these ABH, the gene for this codes on chromosome 9. For H is on, for this one is chromosome 1, for AB is 6, for AB is 9, and for H is 19. H is 19, AB is 9. Is that correct? I think it should be correct. Okay? So each gene is on different chromosome. Okay, for antigen D, the gene is located on chromosome 1. For H, on 19. For AB, on chromosome 9. This gene, okay, has different versions. It's the same gene, but it's different types or alleles. The A type will code for N-acetyl galactosyl transferase. The enzyme is known as what? Transferase. What is a transfer? That's all. What would you call it for B? Galactose transferase. But scientific term is galactosal. I mean, it doesn't really matter as long as you get the idea, right? Okay, are we good? Okay. Now, in terms of the genes, A and B are codominant to each other. They're codominant. That means A cannot overpower. It's not like you can only have A. You can have both of them at the same time. That's codominance. But A, B together are dominant to who? To H. Okay. So if you look, and we've seen that. Look, if H you add to it something, it's no longer H. It just changed. But A, B are two different things. Okay. So you can have on the same RBC one H here. It doesn't mean they have one antigen though. Look, the RBC on the surface, you have multiple H's. Right? These are not like just because I dried one, you don't think of it as one. The surface of RBC has many spikes, many receptors. So there's a lot of, usually I think it's about 25% of the surface of RBC in terms of channel and protein is band, and about 30% is H, unless it's modified. Okay? So if this H exists, a lot of them, there's a lot of spikes of H. Let's say you modified, so this gene, so you have one gene, because you have two alleles, right? You get one gene from your dad, one from your mom. Let's say from mom you get the A gene, from the dad you get the B gene. So that means some of these residue will be modified with galactose, and some of them will be modified with N-acetyl galactose. So you have AB blood. But as soon as you modify the H's, it's no longer an H. That's why AB is dominant to H. You cannot have O and B at the same time. Makes no sense. You either modify it or you don't. But you can modify the H's to A or to B. Both of them can exist at the same time. But as soon as you modify all the H's, if you have the enzyme and you add galactose to all of them, there's no such thing as H anymore. It's done. It's modified. Okay, so A and B are codominant, means they can both exist at the same time. But A and B are dominant to O. That means A and O cannot exist at the same time. B and O cannot exist at the same time. Because either you modify it or you don't. Either you put a hat or you don't. If you don't have a hat, you're O or H. If you put a hat, you're A or B. If you put a red hat, maybe you're B. If you put a green hat, maybe you're O. It's not like you can have a hat at the same time and you don't. There's no such thing. You can say halfway, but still it's a hat. Okay? All right. So I hope you understand the concept of the antigenicity of RBCs. So know that blood cells, red blood cells, are identified based on what tag do they wear. Are they wearing the A tag, the B tag, or the H tag? Okay, that's identifying it at three types. In addition to that, they can have the D tag or they don't. So that means you should have two IDs at the same time, right? Okay. Okay. Let's do this so we can go from here. And then we're done. That's how many? 6? 2 more. Okay. Okay. So this one has A and A, B, B, A, B, A, B. And this one only has H. Okay? So you can clearly identify them, which is type A blood, which is type B, which is type AB, which is type O. Type O is which one? With the H. There you go. So type O blood, type O blood. This is AB. This is AB. It's what IDs you carry. You're going to look, people who have like Mexican and US passport, they're dual citizenship. Canadian and American are dual citizenship. That's what AB means. It depends what IDs you carry. Whoa. They don't like the citizenship idea. Trump, probably. But there is B. Oh, what did I do this twice? Sorry. That should be only B, right? Remind me, because, you know, then you will think I know something you guys don't know. And I'm hiding from you. Type A and type A. Okay, so at least we know the blood typing, right? Now let's go to the positive and negative. And the positive and negative depends if you have the O antigen, which is separate, or you don't. Did I say O? Actually, I should say D. Yeah, the D antigen. So any cell that has the D antigen, they're positive. So that means this one will be A positive, and this one is A negative. B positive, B negative. AB positive, AB negative. O positive, O negative. Total possible blood types are what? About 8 types. Maybe there's more, we haven't discovered it yet, but at the end of the day, when you're being developed, I just remember something. See, I told you you should ask me. Remember when you talk about erythropoiesis? Okay. I told you I want to know what is a zygote. I'll come back to this because I don't want to forget. Zygote, what's a fetus, and what's a neonate, and what's an infant. Do you know the differences? What's a zygote? Fertilized egg. How long does it last? What's the duration of the stage? As long as it doesn't divide to 2. If it's a single cell, it's zygote. So that's usually about 12 hours. Okay? What's a fetus? Oh, before that, I wanted to include in here embryo. Let's just put in embryo. There you go. That's what I was looking for. What's an embryo? So this is from zygote, from 24 hours to 8 weeks. Let's just say this will only the first trimester. The first trimester is known as embryo. The baby in the first trimester is known as embryo. Okay, and then what? Fetus. Okay, fetus. Okay. And what's neonate? Newborn, after birth. After birth until 1 month. Okay? After birth till 1 month, and then infant is from 1 month to 1 year. Okay, and then you have toddler and so forth. But anyhow, why am I saying that? Hematopoiesis, I forgot about this because hematopoiesis, during embryogenesis, during this period, the primary organ is what? Yolk sac. That's the primary organ that produces RBCs. Okay? Second trimester is liver and spleen. Third trimester, which is fetus and neonate both. So let's just say first trimester, second trimester, and third trimester. What time is it anyways? Almost time? Okay. So first trimester, it's in yolk sac. Did you guys ever go to Yolk in downtown? It's a beautiful breakfast place. Amazing. You should. Liver and spleen, and then bone marrow. Okay? That's the dominant locations of RBC production. You should know that because you will be asked. Okay? So during the first trimester of a baby, majority of the hematopoiesis occurs where? Yolk sac. Then it switches to what? Liver. And then in the third trimester until we die is bone marrow. Also, now when we talk about bone marrow, there's something unique, okay? In the first 5 years of life, all bones can produce hematopoiesis, all bones, okay? Up to the age of 20-25, only 2 long bones can produce it, tibia and femur. But after age of 25, long bone stops, only flat bones. I will show you a graph though. The flat bone that is the highest, that's the most active in erythropoiesis, vertebrae. Sternum, number 1. Number 2, vertebrae. Third, ribs, okay? All right. So in adults, just on the side, in adults, if somebody is having hemolytic anemia, most of the erythropoiesis will occur where? Flat bones. Can the flat bones expand, get bigger? Yes. So for thalassemia, when you take an X-ray of the skull, they'll be thicker. The bone will be thicker, not the whole head. The bone, the cranial bone, the sternum, because there's a lot of erythropoiesis. That's some indication. So maybe there's pictures in your book. Look at it. Anyways, I want to finish quickly. Then we're set for today. Last thing is that you know that blood reaction. We have to match blood, right? We have to match blood. The reason for that is, let's say this person, so this person has type A blood. That means his RBCs were exposed to the thymus. During fetal development, all possible antigens in your body are introduced to the thymus. And they're introduced to who? To T cells. And then the T cells that recognize your own antigens, they are killed. And the T cells that don't recognize your own antigen as foreign, they're left alone. That's known as thymic education. So in your development, as you were growing from baby to adult during that period, your thymus was used, even now it's used, for educating your T cells. What are you going to teach them? You're teaching them, look, these antigens are my own. Please don't attack it. They're okay. But these antigens are foreign. So whenever a T cell recognizes an antigen as a foreign, that T cell is killed, so it doesn't act on against you. For example, if you have a cop that kills us, what do? I mean, not exonerate them, we should jail them, but whatever. You get the idea? So that means if you have type A blood, you have the A antigen. Are your T cells, your immune system, is it aware of this? Yes. So this antigen is not a foreign thing to you. You have seen it before. The D antigen in this case, have you seen it before? Yes. So if you give this person type A positive blood, to him there is nothing new. I have seen the A antigen before. I have seen the O antigen and the D antigen before, so I'm not going to produce antibodies. The only time you'll produce antibodies in response to something is if you have never seen that thing before. For example, if we see a creature that you've never seen before in your life, what would you do? You'll panic, you'll scream. You're going to call people, hey, help me, something is happening. Same thing, your immune system, when it recognizes something that's not yourself, will attack it. But when you give a positive person a positive blood, they should have no problem because there's nothing new. They've seen it before. What if you give them O positive? No problem. They have seen the H antigen has no immune reaction. So the H antigen is not recognized by a T cell. So there's nothing new. They've seen D before and in O negative. So A positive people can receive blood from O positive, A positive, and O negative. No problem. Nothing is new. Huh? A negative, sure, yeah. A negative, excellent. Okay? Now, let me do the extreme cases, and then the rest you can do yourself. Okay? O negative. If you give them O positive, has O negative person ever seen the D antigen? No, suddenly they come in contact with, oh my God, where's this D coming from? This must be foreign. Let's attack. Okay? So O negative can only receive from who? From O negative. No one else. Okay? Let's go to the other extreme. AB. AB can receive blood from who? From everyone else. Because there's nothing they haven't seen. Okay? So hopefully, just play around with these scenarios. Who can receive blood from who? At the end of the day, the last thing I want to do is type A person. Type A person. Let's give them a big abdomen, sorry. I just want to make sure that it looks like a container. Type A person. Type A blood. If he receives blood from type B blood, what would happen? Number one, IgM will come in clump. Number one, clotting will occur. So IgM, which is a pentamer. Remember that? Okay, so number one. So if you receive type B blood, you're like, I've never seen this B antigen before. So your IgM will come and attack. But IgM is a pentamer, correct? Excellent. Good job. So how many RBCs can IgM bind or trap? Very good. Let's say a lot of RBCs. Good. So here's one, here's another one, here's another one, depending how it happens. So number one, you trapped all the RBCs. That's what the clumping occurs from. because the RBC is no longer freely floating around. They're clumped together. This term is known as, what do you call this process? Clumping, coagulation, clotting to an extent, but agglutination is the best term. Agglutination. Okay? When an IgM or an antibody bind many RBCs at the same time, and these RBCs are clumped together, that's known as agglutination. But of course, IgM is not going to bind your own RBCs because they've seen that before. You don't have anti-A antibodies in yourself. You can only produce antibodies in response to something that you've never seen before. Okay? And then IgM activates who? Complements. Complements. And complements will cause what? Hemolysis. So that's transfusion reaction in short. Okay? But you should match them A, B, C to see what happens. There's two things that happens: agglutination and hemolysis. If you have diffuse hemolysis of many red blood cells, what happens to your ability to carry oxygen to your tissue? Goes down. And you will grasp for air. You will have difficulty breathing. You'll have tachycardia. You'll have a lot of symptoms. Okay? Yeah.
Would it matter if GPIC matter at all?
In this case, it wouldn't matter. Yeah. Because they're already tagged by who? IgM. Yeah. Good question. Okay. So there you go. We're done with this part of the RBCs. Tomorrow is the most important day in all of RBCs, more than anemia themselves, and that is hemoglobin synthesis. Please study hemoglobin synthesis. Hemoglobin heme breakdown, heme synthesis, and the hemoglobin curve, and types of hemoglobin. Okay? All right. Good, good, good.